one thing I wanted to show you is, welcome back, I should say, to the recording that you'll see if you watch this again, or the random people on the internet, of which one gets to watch my stuff. When it comes to the argon problem, I'm still struggling with libraries. So there's one more workaround I want to show you real quick. Here, I need to mount this. I'll just make this quick. I'll make this larger in just a moment. As it starts up. So I got this argon thing working. I mentioned I had a couple students who was grateful for their help in testing it. And then, of course, it didn't work for what you were doing. So let me show you the workaround I have. If you build in the following. So last week we all created an R-environ file that had this rlibs user pointing to a directory. The problem that R has, if it hasn't installed a package yet, is it tries to take one of the first, this is the third directory on that list. Do you remember that? Like the third, if you do lib paths in R, that function, the third one was the one we created. Right now we have to point R to that folder to install. When you load a library, R goes through all the lib path folders, of which that last one we created, and finds the library. But for now, you need this lib statement. I believe I can fix this with another Aptainer image. If I build this into the path, the environmental variables in the Aptainer, and it points to a same folder on your disk. But I'll have to test it out, okay? So we're gonna keep working on this. Ironically, I'm a subcontractor, subaward from a grant at the University of Florida. One of you has worked on this. Actually, several of you worked on several things of this before. Yesterday, I'm putting an adaptive algorithm for a diagnostic model on a server. This server is a Linux server, so I'm SSHing in. Why this matters, by the way. Guess what? I didn't have write access to any of it with the exception of one small folder. So the stuff I had to teach, the workarounds we've had in class, guess what I did? I got to go and use the lib, and I pointed to that folder, and then I did lib.loc in library, and I pointed to that folder. And it worked. And the server is now, well, they're configuring it for what we do. By the way, I'm using something called rplumber. Anyone ever heard of rplumber before? I know you're like, how much better does it get? RP lumber, yeah. rplumber is a way to take R, put it on a server, and have it sit behind access point called an API, Application Programming Interface. So it will allow you to have something where this app, students are going to be taking items on this app. Every time they take an item, we got to figure out which item goes next. We have an adaptive algorithm, and it sits. I just coded it straight in R, but I put it behind a little bit of plumber commands, and then the server guys, server people, hooked it up to make sure it pointed to the right spot. So now anytime you can send it data and get it back. So anyway, just down the rabbit hole of technical. Why I'm saying this to you is to try to motivate our use of argon. You never know when it shows up. Like when you have to switch over to Linux mode, or you have to switch over to what other mode. So knowing a little bit more of that will give you a lot more, you'll be much more valuable to those employers who may want to make money off of what we do. That's all. Or you might be like me and be like working in academics, have a grant, and someone's like, hey, I need an adaptive algorithm. What do I do? Don't contract with the vendor. You are the vendor, all right? So now on my recording, by the way, the vendors are not being mentioned. So, all right, questions? Comments? Complaints? I know it's hard to complain to the guy giving you the grade, but I promise there's an algorithm for the grade, and I don't have the time to do grade disputes, so I'm not going to be super grumpy about it. I do like your complaints because I want to make this better. Customer service. My first job, that wasn't like coaching flag football, was in a fast food place called Carl's Jr. in California. And I kid you not, how many of you have worked like fast food jobs or jobs like that? Like you go in and like the training for it is a bunch of videos. Did you ever have that? Like we had videos. I still remember they called it WOW service. It had some dumb acronym for it. So it was like completely corporate Dilbert whatever. But I tell you not, I kid you not, that training in customer service for fast food prepares you excellently for at least administration and academics or working with them. All right?
At McDonald's, our official titles, all the people who worked there who weren't managers was customer service specialist.
This is it. It was all about the experience, which really boiled down to, yeah, someone may be mad at the situation, but they're not mad at you, number one. And number two, when you screw up, apologize and give them a cookie. All right, and those two skills, like understanding that goes a long way. I don't know how I'm on this. Am I wrong? What did you work, Sergio?
So I worked at the Einstein's Bagels and Caribou Coffee in the main library at UGA.
I know of that place, yes. I used to work at UGA, for those of you who didn't know that, but yes. Yeah, it's a hard job to have.
Closing shift during finals week.
Oh man, that's rough. Yeah, getting the kids out when they're having to study and stuff. Or whatever. All right, so plans for this week. I've gone a little overboard on the slides. So today's got a lot of slides. So we're not gonna have coding this week. But next week is all about coding. So next week what we'll do is I'm going to show you how to do a confirmatory, explanatory, set of confirmatory models and explanatory models and model comparisons in 5 programs. And why am I doing 5, right? Because you never know when one of them has the exact specification that you need. So we're going to do M+, we're going to do Levon, we're going to do Levon's a package, MERT package, and then we're going to flip over and do JAGS, which is a program with a package in R, and STAN, which is a program with a package in R. The JAGS and STAN, I know there's a couple of you who weren't here last semester, maybe not even students, who didn't take, not last semester, last fall when I taught Bayesian, so it'll be sort of a really rapid intro to those, and later on in the semester I'll give you more time if you want to, but I'll point to some materials that might get you familiar ahead of time. As you know, we have a whole class on Bayesian because STAN takes a lot to get into. Am I right? Bless you.
Thank you.
Would you summarize STAN as being not user-friendly? That's a good summary? Everybody's laughing. Wait till you see JAGS. So it gets worse. So that's the plan next week, okay? And then what was supposed to be the next 2 lectures I'm sort of consolidating into one. So next week will be how we estimate in all these programs. The following week will be exploratory versions of models. And will be another data analysis homework that comes from it. There is a new homework assigned this week that's going to take estimation and let you do estimation. I will also reiterate in this week's homework, you are allowed to work together. It's okay, all right? And I'll say this also, the tough thing about working together, I think this week's homework's a bit of a challenge. I'll get to, well here, I'll just say it now. I wish I would have learned this when I was in your shoes, because you'll be surprised the time this type of thing pops up. Oh, it's an icon, isn't it? Anyway, the goal is this. I want you, there's a thing. Oh, it was? Okay, yeah, it's basically do tetrachoric correlations. Build a likelihood for a tetrachoric correlation, put it in a function, wrap that function in another one that does optim, like optimize it, find the maximum likelihood estimate, and then use that on your data. That's a lot, but I know you can do it. But the end of this lecture has the tetrachoric. So let me see the assignment real quick. Anyway, but you can work together. But here's the one catch. When you work together, you can even copy each other's work. I need your honesty to say that you actually contributed to working. The other thing I will say is, if there's somebody who would like to work with somebody else and may not have a group, maybe because of whatever, be kind and try to bring them into whatever group you're in as well too. So just look out for each other. Okay? Does that sound good? Okay. All right, you ready? Should we do this? Estimation. You like estimation? Yeah? Oh, thank you, Tolga. I appreciate that. Does anybody hate estimation? Estimation is difficult. I'll just put it that way. We have a lot of this stuff here. Nope. I I didn't cut the notes out. Anyway, that's coming up next. This is what we're doing. All right. So I started building these slides, and I thought to myself, you've all had a lot of classes, but I don't think you talked a whole lot about maximum likelihood in each of those. Like, for instance, I know in Lisa's slides, because I refer to them a lot, she talks about, oh yeah, here's a likelihood function. Like, she'll show it to you, right? I don't think she derives where it came from. Like, that's the distinction. So I want to describe where it comes from for you. And we're going to take a very basic example of maximum likelihood. And then we're going to get into, so the first part of this class is how maximum likelihood works and why we do it. Hope that's alcoholic. Can we bring a beer to class? Crack in some cold ones? That would be great. We have a fridge. That's right.
Kombucha.
Okay. Okay. Well, look. Whatever.
Actually, there is alcohol in kombucha. Now that I think
Kombucha, right? Yes. But so I thought to myself, it'd probably be good to give you the primer that I like to give on maximum likelihood first. Right? If I asked you to build a likelihood function, could you do it? How many of you? What's the likelihood function in a multi-level model, Nathan? How would you build it?
I do it perfectly in Stan.
Okay, that's Stan.
I know how to specify it in Stan.
But I'm talking about it to now and find the optimal, the peak value based on the parameters.
It's...
See, the stumble.
First derivative.
No, not there yet.
Nope.
What's the function you take a derivative of?
The log likelihood function.
And how do you build that?
You maximize...
No. So that's why. That's why this section is... Not that, Nathan, you're our... And by the way, I'm putting you on the spot with very bad questions. So take nothing about those answers to reflect upon Nathan. It's more the question asker. But this will help. My strategy was, let me just dive into MLEs first. It's a core part of what we do. And anytime that you want to do something different, you're going to need to build a likelihood, usually somewhere. Now, you can rely upon Stan, you can rely upon other programs. That's great, but I think having this skill will augment what you do as well, too. Okay? So we're going to talk about maximum likelihood estimation. We're going to talk about how it works, why we use it. We'll talk a little bit about robust ML and implications for missing data as well. Because estimation and missing data actually have a big hand-in-hand connection. But let's talk about why an estimation is important. Now, I know this slide is silly because we're all in the same field. But many of you don't have the same focus I have, and I appreciate that. It's fine. You don't have to have my focus. It's not a big deal. But can we all agree estimation is really important? Here's a dumb example, right? Imagine well, first of all, it's hard to talk about this in applied stat because it's really technical, and it can be very intimidating. There's a lot of calculus. Not the calculus that we're going to do. You're not going to be doing calculus this week, I promise that. You might be using results of calculus, but we'll get to that at the end of class. It'd be very intimidating to do estimation too. And let me be honest, right? A lot of these algorithms, I'll have to study for a lot myself to do, right? That's just who I am. I wish I knew everything. I can't. I don't. There's always, every one of us has a different math continuum that we're on. There's always people who know way more math. At least there'll always be a better basketball player to me. There will always be a better mathematician than me. There'll always be, that's just how it works, right? But I'm still unique in my own way. That's okay. That's not to say, what I'm saying that for is, if this is technical to you, don't let that, if it's hard for you, don't let that be a reflection of your self-worth. Don't let it bother you. It's hard for everybody. I've been doing this for a lot of years. It's still hard, okay? Okay. But it's critically important because the quality and validity of estimates and how we use them depends on how they were estimated. Let me give you an absurd example, right? Let's imagine, remember IQ? There's an IQ scale, Stanford Binet, mean 100, variance 15, standard deviation 15. Remember that? The IQ scale, the old classic scale of IQ, gone around for years. What if you collected data and you came to me and you didn't know anything about, you were a person before you knew anything about data. You had it all in Excel and you're like, hey, what's the mean of my data? And you give it to me and I'm like, mean's 20. Mean is 20. That'd be a little weird, right? You have this impression that the mean of the scale should be somewhere around 100, and I tell you 20. Why is that? Well, that's because I am an estimator. Anything can be an estimator. Any one of you can be an estimator, right? It's terrible. We all make subjective estimates all the time. Our subjective estimates lack the theory that statistical estimates give us. And that's the key about maximum likelihood. Maximum likelihood, the M should actually stand for magic, because there's some magical properties that happen. I know that sounds funny, but seriously, like, wait till we see these properties. There's some legit, like, why we use maximum likelihood stuff going on, which is really important. So let's talk a little bit about how estimation works. I've tried to round it into 3 things. You may have seen this in Lisa's class. By the way, it came from me first, and I'm taking it back. All right? So when you see this in Hoffman's class, you're like, hey, you took that from Templin. Now 90% of what you see from her class I took from her. This one's mine, all right? This one's mine. All right, 3 things that estimation we usually do mathematically to estimate. We either minimize something, right? We either maximize something, or we use simulation to sample from something. I had to put something in there because I'm giving you the general introduction first. Next slide's going to be integrals, but we're going to do something right now, okay? Minimize something. So what do we mean there? How many of you have heard of ordinary least squares? Least is the synonym for minimize. The process is minimizing a squared, some type of square loss function. There are other terms that show up in minimize. Generalized shows up everywhere. Shouldn't put that there. Weighted can show up everywhere. Diagonally weighted, iteratively reweighted. I like to think of this as an estimator of last resort due to less desirable properties than ML estimators, although in some cases least squares and ML are identical. One of those cases is linear models, linear regression. Your MLE and your least squares estimate are identical for the point estimates. The big question then is the variance. In MLE, the variance is biased, unless you use Rummel. Maximize something is the next thing. So think of it this way. Do we either have a function that describes like how far off we are? That's minimize. We want to minimize the distance how far off we are. Sometimes those functions are called discrepancy functions. Maximizing is the opposite. Instead of minimizing, we want to find the maximum. Well, usually this involves maximum likelihood, right? And that function that we're maximizing is a likelihood function, right? Yeah, Sergio, you got a thought here? No? Oh, sorry. I was like, I'm like tuned in. I noticed every part. No, I don't actually notice that much. So we find the word maximum showing up here. Maximum likelihood, marginal maximum likelihood, residual maximum likelihood. How many of you love a good Rummel estimator? Rummel, by the way, is pretty amazing. That version of maximum likelihood gives you unbiased variances in linear models. And then robust maximum likelihood as well. Maximum likelihood, I think, is the gold standard still, even though I prefer the Bayesian estimates for what I do these days. But you'll see why I don't really mind maximum likelihood in just a moment. Finally, simulation to sample from something. Those of you all took my Bayes class, you know what that is, right? Markov chain Monte Carlo, what are we sampling from? The posterior distribution, correct. And then there's all sorts of names from that. Gibbs sampling, Metropolis Hastings, Hamiltonian Monte Carlo, and then Monte Carlo itself. You may even combine some of these. You could, if you took a bunch of bootstrap samples of your data and every single one of those you applied an MLE, that's sort of a combination. Right. So this sit with what you think about estimation, how it works, generally speaking? Yeah, all right. All right, what's so good about ML? Properties. There are a set of assumptions that we tend to make in ML, 7 or so. They're called, by the way, statistics, this is the reason why data science people are all running around like being real popular. It's because their words are better. Like in ML, instead of saying assumptions, we call them, regularity conditions. Like, it's a terrible name, right? Regularity, like, anyway. But that's what you see. So if your data meet these conditions, or the model meets these conditions, you get these properties with ML, and this is the magic for me. One is called asymptotic consistency. Let me break that first word down. Whenever you see asymptotic, you can replace in your mind what happens as n goes to infinity. Right? As your sample goes up, what happens to the estimates that you get? Consistency means that, actually, asymptotic consistency. Consistency means basically, are you going to get what the true value of the parameter happens to be? Right? So asymptotic consistency says, as the sample size increases or goes to infinity, the estimator converges in probability to its true value. Right? So there's a chance, and that probability goes to 1, effectively. Right? So that's a good thing, right? ML with a likelihood function, so long as you meet these assumptions that are out there, which are pretty easy to meet in most cases, you get the right answer. Your sample size is big enough. That makes me feel good, right? You want that. Asymptotic normality is next. Now again, what's asymptotic? Anybody? N goes to infinity, right? Like literally, the limit as n goes to infinity is an asymptote. Normality is pretty easy. What this means is, as the sample size increases, the distribution of the estimate are normal. In fact, not only are they normal, we can determine what their variance or standard deviation happens to be using an information matrix, an inverse of an information matrix, which is a second derivative from a likelihood function. So not only is it normal, we can also talk about so the mean of it is at the parameter, the variance comes from other parts of the likelihood function, right? Now all of a sudden we have a framework in which we can test hypotheses about parameters as well, right? And so maybe you've heard of the Wald test before, where you take a parameter and divide it by a standard error. Maybe some of you have seen this in Lavon or M+. There's a p-value at the end, right? It's usually parameter, standard error, parameter divided by standard error, and the p-value. You know that p-value, guess where it comes from? The z-table, or the like the standard normal, right? Because if you take a parameter divided by a standard error, that part from normality says that number should be standard normally distributed. That's also cool, right? It just falls out. It's a way of testing things. Finally, another really good part of this is efficiency. No other estimator will have a smaller standard error. That's really good too, right? So now you've got the best precision, and you know if you collect more and more data that you'll get the right answer, and everything will give you a framework in which you can test hypotheses or otherwise evaluate things. And all that comes from the likelihood function itself. So whether your likelihood is multivariate normal like in CFA, or it's multivariate Bernoulli like in line of response theory, if you take the maximum likelihood, you form a likelihood function and maximize it with respect to the parameters, you get these nice benefits in most cases, so long as the assumptions are met. Isn't that cool? I think it's cool. That's the magic to me. I'm not giving you the proof for all this, but you can go get that in the math stat classes. I like to take their word for it for most of what I do, but that's pretty good stuff, right? Those of you who took stat, have you ever had to prove any of this before or show it?
Yes.
Yeah.
It's terrible.
It's hard, really hard, but we can use this to our benefit, right? The other thing I will point out, asymptotic shows up. Asymptotic is an interesting word because it's the limit as n goes to infinity, right? Where's the limit? Where's the asymptote? And oftentimes what we end up doing is fighting over where infinity might lie. I heard this from Rod McDonald my first semester in grad school, but he's absolutely right. Remember the t-test? Way back when, like a one sample t-test, and they had degrees of freedom of it. Once the degrees of freedom hit about 25, it no longer looked like a t-distribution, it was pretty much a normal distribution. That's like the visual of asymptotic normality, right? The t-distribution has like a little bit fatter tails, and it starts getting closer and closer to normal, and eventually it becomes normal. That's like what happens. The hard part is figuring out what n is enough to believe it, right? So that what we call, like, if you use this result, you're assuming asymptotic convergence. Basically, you've gotten enough sample that the asymptotic distribution is close enough to normal to use in what you do. And nobody that I know of can really confirm that or not. You can't really tell. So for any finite sample, it may or may not meet these properties. But that's what happens. And that's actually the distinction between a little bit of what we do in ML and what we do in Bayes as well, too. How are we doing? Is it interesting to you? Cool. All right, let's talk about where we get a maximum likelihood function from. This is very simple. We're going to start with a univariate normal distribution. We're going to say x follows a normal distribution, has some mean, has some variance. It's nothing to do with psychometric. It's a single distribution. All right? This is the probability density function, sometimes called PDF. You've heard me talk about that before. In Bayes, it's like all we talked about was PDFs about whatever, because that's how we build things. But just think about it mathematically. What happens? You plug in x, you plug in mu, you plug in sigma, and it returns a number. There's a graph of it, right? So you can see for varying mu's and sigmas, this is the shape of what you get. The height of the curve at that point is called the likelihood, right? It's like a relative frequency. Right? How likely or how frequent, like a -3 were to occur when you have the green line right here, right? Why is it relative? Because the y-axis here, the function itself, I don't know what I'm doing with this character set, but this function right here is defined, it defines it across the entire distribution itself, across the entire range. And so relative to a -2, we'd say a -3 is less likely because it has a smaller likelihood. That's what it's used for. The likelihood of them itself in a continuous distribution is not easily interpretable, right? You can't say just because at -3 it looks like the value is 0.2, you can't say you have a 20% chance of getting a -3. That's not how it works with continuous measures, right, or continuous distribution. Technically speaking, the value of any discrete point is 0, the probability of that, because the integral from a to a equals 0 by definition. You need some small epsilon around a point to figure that out. How are we doing? So that's a likelihood function. It's also a PDF. So let's plug in some numbers. Here's a mean of 100, variance of 189.6. There used to be data that went with this, but I threw the data out for the day. I'm just sort of talking theory today. You can tell 100 is more likely than an 86. That's what we see with this. Sounds good? Now note, with each of these examples though, we've held constant a mean. We picked a mean, we picked a variance. Here, different means and different variances for different colors of the curves. Here, one mean, one variance, different heights, right? In practice, we don't need to know the height of a hypothetical x. We observed an x, right? We need to know what the mean and the variance happen to be. So it turns out the likelihood function of the PDF uses, that's where a PDF moves from being PDF to being more like likelihood, right? The likelihood of these, the data given these parameters themselves, the likelihood of the parameters given the data, depends on how we describe it. Any questions? Am I boring you? No. Okay. Annette, maybe. But the rest of you is okay. Just kidding. I see the smile.
I just think it's funny that you ask.
Well, I can throw explosions in here.
That would be cool.
Yeah.
Just like, that's how all your slide transitions should be.
If I could, if somebody can find a Reveal.js slide transition with explosions, I'll take it. Fireworks. Let's make it like a fun explosion, like fireworks. Yeah, Vladimir.
Yeah, can you repeat please? In the previous slide, you said that in that case we shouldn't interpret that height as the probability of something, but as the likelihood of
That's
that
correct.
value.
That's right.
However, in the previous slide, when you have that thing, your y-axis is from 0 to 1, which is a probability.
It is, but not all distributions follow that.
Oh.
So let me talk a little bit about PDFs. Thank you for asking that, and I should have put that in the slides. Things that I tend to forget because it's been drilled into my head. I need to remember learning. So this distribution, to be a density function over a continuous measure, you have to integrate to 1. Okay? This does. It just so happens that with this value of parameters, the maximum is less than 1. But if you picked a variance that was 0.002, guess what's going to happen to this curve? It's going to go up, 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 and it'll go above 1. So this is why we talk about this not being a probability. It's relative to the space that it's over itself, right? Another way of looking at that is if we have a uniform distribution, right? So uniform distribution, this is x, it goes between some a and some b, and this is f of x right here. The limits, the PDF itself is basically, this is a rectangle, effectively, right? And so this area has to be 1, right? So the area of this is length over width, length times width, right? So length of this is b minus a, right, times some f of x itself. Basically what you're getting here has to equal to 1. What you're getting here is the distribution function itself. If you pick an a and b that are really close to each other, that height is going to be super high because the width itself is not large, but the height has to be to make it make the product equal to 1, right? Yeah. So this is a bad example. I'm not as prepared for that example, but that is the key in looking at this, which is there will be distributions for which the y-axis has values like 27 or 24 or whatever, right? It depends on the type of data, it depends on the type of assumptions, and that's why it's relative frequency and not a probability.
Great.
Thank you. All right, so MLE, maximum likelihood estimation, begins by building a likelihood function. That function before is a PDF when we plug in its parameters and look at x. It's a likelihood function when we plug in x and look at its parameters. You see the flip? Think of it this way. To draw this curve, I fix values, or draw these curves, I fix values of the parameters, and I vary x, right? That's the PDF. That's the density of the distribution across x. But mathematically speaking, this is just a mathematical function. We have input values and output values, right? So in theory, let's imagine I plug in x, and let's imagine I have a stroke of, like I got hit by lightning, and I have this magical power that I happen to know the variance precisely, right? And so I plug in x and I plug in the variance. Guess what I can do now? Instead of having x down here, I have mu. I have the likelihood of mu conditional on my x, and I happen to know the variance itself, right? And so typically the language that we use when we're plugging in x, we're looking over x once we fix the parameters, that's PDF. When we flip it, when we observe x and we're looking for the parameters, that's now a likelihood function. But the function is the same. It's all about the distribution itself. Does that make sense? So we start with the density function. The one that you just saw is for a single observation, right? Well, it turns out when we collect data, there's not a whole lot we can do with a single observation. For instance, you can tell the mean of a single observation. It's pretty straightforward. But what's the variance? You can't, right? It's a single observation. It's a constant. So we need a likelihood. We need to take each observation's PDF and combine it into the PDF or the density, the likelihood for the whole sample itself. And that's the key step in this process, is how do you go from one observation to many, right? When you do that, the sample likelihood can be thought of as a joint distribution across all the observations itself. Remember, joint distributions, we talk a little bit about that. Multivariate normal is a joint distribution, right? We have multiple x's. If we think of it from the PDF side, those multiple x's, we talk about the likelihood of observing x1 and x2 and x3, like our data conditional on the mean vector and covariance matrix. Here, the flip happens. We have a whole data set, a whole matrix of data. We can talk about its likelihood, or the likelihood of these parameters given those data as well. But let's take a look at this. So here is our one observation likelihood function. It's silly with one observation. It's actually not a good idea, but I'm using this to try to teach where it's going, okay? Let's imagine we observed an IQ for a person that was 112. So we know x. And like I just mentioned before, I know the variance to be 189.6. I'm that good, right? I'm so precise that my subjective estimates of variance go to at least one decimal place. Now, if you can beat me, hats off to you. But I just happen to know that, like significant digits right here. Never mind. So I have to do that because, as you know here, if I'm looking for a quantity, I have one equation. I need to have one unknown. It's another linear algebra type idea, right? System of equations. One equation, I need one unknown. So I have x is what I know, and I have sigma squared, and I'm looking for mu. So now, this is the likelihood for mu. Now the notation changes a little bit, right? We say this is the likelihood of our parameter mu conditional on our data and us knowing what the variance is. That's what you read the left does. And the right-hand side, all I've done is plug in a number for x and a number for sigma squared. And mu is left alone. Right? So, it turns out, now I can plot the likelihood of mu across a range of values, and I will get a distribution for it. In fact, guess what my distribution is? It's normal, right? It's going to have to be normal in this case because that's a normal PDF right there. Right? Questions? So what do you think the maximum likelihood estimate of the mean will be if x is 112 and sigma squared is 189.6?
The same number.
112. The reason for that is x mu shows up right here. And if you look at this exponent, we're taking Euler's number, Euler's constant, exp, and raising it to a value that's negative, unless, of course, we put something that's 0 in it, and 0 happens to be the biggest number there. So that'll maximize the exp part. How's that sound? Hope that's right. Okay, I'm rusty at this stuff. It's been a while. I used to teach this in multivariate. I enjoyed, I used multivariate to build likelihoods, but I don't teach that here, so forget it. All right, how are we doing? There's our distribution. There's mu. Here's our likelihood itself, right? And you can see the point of that is 0.029. The value of it is 0.029. So that's, we would call 112 our maximum likelihood estimate. Sorry for my LaTeX typo here, LaTeX typo. Slide 16. I'm making my typo list. That value, again, is somewhat unnecessary. We just need to know that that's where the maximum occurs at 112. That's it. All right, but the process, though, of finding it gets us all sorts of craziness, right? Like if I gave you just this shape of this right here, how would you go about trying to find that the maximum of it? First, we got the calculus side. Yeah, that's right. So if we were looking for a line that's, so this is it. If you haven't a calculus, don't worry about it. I'm going to give you the quick calculus. Okay? The first derivative is the slope of a line that's tangent to this curve. By tangent, you think about take a single infinitesimally small little region, draw a line through it. That slope of that line is given by the first derivative, right? So we want that line to be flat. So we want that slope, like where this dashed line is right here. If we just extended that out, that's a line that's tangent to our curve that has a slope of 0. So that's where calculus comes in handy to take our first derivative, set it equal to 0, and solve. That's great. Who has the time for that? Come on now, we're in the real world. We're talking about technical reports and model fit and large-scale assessment. If I told you can't use calculus for this, next, how would you do it? But you can use a computer.
Grid points.
Grid points. Yeah, a grid search. Basically, carve up little intervals, plug in values, see where the trend changes, right? Yeah, perfect. That is that will find it. It may take a while, may be inefficient, but given the way I do calculus, it probably is going to go faster than me. So,
That's what functions are for.
that's what functions are for. That's exactly right, right? Okay, why I'm saying this is there's the math side of it, right? So if you're working in the stat department, if you go take stat classes, generally speaking, now stat's a huge field, so there's all sorts of things. But you take some of the theoretical stat classes, you're deriving this distribution, or you're deriving likelihood estimates, or using calculus to do that. That's fine. But there's a huge disconnect between the analytical math that you're doing and then the computing that goes with it, right? And computing is what we're going to do with this. But to do the likelihood, to figure out the maximum of that likelihood, we're going to have to first know what the function is. I'm now describing your homework, just in not that many terms. We're going to first figure out the likelihood function, and then we're going to let R do the grid search for us, although it's going to use a little bit more fancy of a search. Okay? Okay. But that's only one observation, and this was a dumb example. Dumb, I mean, I don't know if the dumb is the right word. I'm okay calling myself dumb because I live with me every day. I look in the mirror, I know what I'm getting, right? But let's be real. It's sort of a trivial, I sound like an academic now. That was a trivial example, right? It was just, it would never work in practice. You're not going to collect one piece of data and be like, look, my MLE for the mean. Yeah, whatever, that's not going to happen, right? So we got to go and figure out how we combine the data into a joint likelihood function, the sample likelihood. So that's what we have to work with. We have to make some assumptions, right? So literally what we're thinking about is if we assume, and again, this is a simple example, we're just collecting observations, right? If we assume we sampled people in a way that is so that each person was independent of each other, right? So that, we have, these are IQ scores, we just randomly grab an IQ score of people. And we assume that each one of those distributions of that score is identical, right? So, I mean, Vladimir, you're normal, Ahmed's normal, Mubarak is not like Kaushi, right? we don't want to have that happen, right? So we want everything to be assumed. If we assume that, then by independence, first of all, if we assume all the distributions are the same, that means we can take our joint likelihood and break it into a part for each person with their respective x, right? So Vladimir's IQ, Mubarak's IQ, Ahmed's IQ, and so forth. That's the independence. Multiplication comes from independence. It's just like flipping a coin, right? If you want to talk about observing two heads, we assume the coin flips are independent, and so it's the product 0.5, the first flip, 0.5 for the second flip. This is just independence, but instead of coins, we have distributions of data. It's the same idea. Here, pardon me, question? No, okay. So the question is, what's the form of the distribution? So again, if we assume everything is identically distributed, that means this is normal for Vladimir, normal for Ahmed, normal for Mubarak. Sorry to pick on the three of you, but you're right up front, so that's where it goes. That right there is what we have to do. So now we have a mathematical way of doing that. We just take the product across each of the distribution functions. That product, we plug in our normal, right? Here I should have also put X should have a subscript P on it right there. This is slide 17. Sorry about that. All right, but if you do the math, if you do some exponents and so forth, you'll find that that product can be re-expressed in this term right here. All right, so now we have a, what did I just do? Please? Please? Make sure OBS is working. It is. Okay, sorry about that. My elbow, I gave a little forearm to the input for the TV. There we go. Sorry about that. I should stand over here. I notice on the right-hand side they're looking around the computer like they tend to do, like I always stand in the way, so I'm just going to stand over here. Problem solved. Okay. So here, this is the form of the likelihood function. We've observed the x's. We don't know mu and we don't know sigma squared. And you'll note, this is the likelihood of our parameters conditional on the data. That's how it's described. So, how are we doing? So, first step, figuring out what the single observations distribution is. Second step, defining the assumptions. Independent, identically distributed. Third step is taking the product. We good? Okay. So, turns out this likelihood, remember, Vladimir, you pointed out that our normal distribution has these heights that are very small, right? This value, 0.028. If everybody's in that range, let's just assume that this looks like the range where we find a lot of our data, right? If everybody's in that range, it turns out we're going to be multiplying really tiny numbers together. And every time we multiply a number that's really tiny with another number that's really tiny, it gets closer and closer to 0. So that can cause the computing systems a bit of a problem. So often what we do is not maximize the likelihood function, we take the log of it. Remember, the log of a number between 0 and 1 is a negative number. So generally speaking, for most of what we saw on that last slide, or if our heights are all 0.02 or something like that, we would expect each person's contribution to that likelihood to be negative, right? What I mean by each person's contribution is, that's person 1's likelihood, that's person's 2. Take the log of each of this. Now, remember, the log of a product becomes a sum of the logs, right? So this is no longer a product, it's the log of person 1's contribution plus the log of person 2 and so forth. Now we're adding up negative numbers, but they're not approaching 0 as we keep adding them, right? We still may have an issue with precision. If we get too negative, right, there's a minimum floating point number that each of our systems ends up having. But it usually is easier to work with. The other thing is, it turns out that log likelihoods are also really nice, particularly in normal distributions, because it turns out that the log of this exponent just takes everything in the exponent and leaves it as it is without any function of it. So it's very easy to work with a normal distribution. It just turns out that log actually happened before we got computing involved in this. Like philosophically and historically in statistics, log likelihoods were just easier to work with normal distributions back in the day before we had computers. They're also convenient for computing as well too. So, as I mentioned just a slide ago, for relatively, I put it in quotes, simple functions. By the way, this is a relatively simple function. Does it look simple to you? No. But that's one where we can actually use calculus to figure out what the maximum is. And here, if we're looking for the mean, you'll be comforted to know that the maximum likelihood estimator of the mean is the sum of x over n, which is the formula that we normally use for the mean. It actually shows up in like almost every distribution. But what we might use is other efficient methods or search methods to find what we call optimal parameter values. So the definition of optimal, this right here, optimal parameter values, are the parameters that maximize the likelihood. So if you hear me say optimal, that means where the peak is, what the maximum likelihood estimate is. Does that say okay? Sound okay? There are methods. One of those methods is called, a historic method is called Newton-Raphson. So basically, instead of doing the grid search that Alfonso had suggested, we could take some information about our likelihood function, do a little bit of calculus on it, and search a grid as well. In fact, this is a Newton-Raphson algorithm. If you start here with a guess as to what your parameter is, your updated guess is the likelihood function divided by, evaluated at the parameter, divided by the likelihood function, the first derivative of the likelihood evaluated at the parameter. That gives you an update. Eventually that will figure out the peak. That's one of the cool things about Newton-Raphson. We will see Newton-Raphson very soon. In fact, there's a function in R called optim, which allows you to use it without having to do a lot of the calculus. Newton-Raphson requires some calculus, but let's be honest again, who has the time for that? I'm saying that jokingly. It is pretty, like building the likelihood's hard enough. Now differentiate it with respect to the parameters. But people do. You get well paid if you do that, usually. But what we can do instead is, if we don't have the matrix of derivatives, we don't actually compute this, we can try to arrive at numerically. We can approximate it using little differences or other methods. and those approximations are sometimes called quasi-Newton methods. We don't have an actual matrix of derivatives or Hessian matrix that we're worried about. This is more numeric, right? Numeric, when I say numeric, that means the computer trying to guess what the derivative would be by taking small changes around a parameter value, like little epsilons, and evaluating the likelihood. Questions on any of this? All right. So that's to get our point estimates. We figure out the maximum. What about the standard errors? We need to take something called the information matrix. Now you've heard information. You took IRT, you heard information, Fisher's information, right? That information matrix and what we're doing here is identical. What you're taking the derivatives of are different. In IRT, to figure out information, I'm thinking you looked at it with respect to theta. It's probably where you heard information. Is that right? Item info, with respect to an item also. There's test information, item information, but each of those, let's take item information. You remember how you arrived at item information in IRT? Anybody? You took your item response function, right? You put it into the Bernoulli likelihood for binary data. You took the first derivative of that with respect to theta, the parameter of interest, right? And then you took the second derivative of that with respect to theta, right? And you could express the likelihood or the information an item has based on the second derivative. And then you summed across items to get like the test information. Well, that process, what the likelihood is, comes from taking derivatives of our likelihood functions, or what the information matrix is comes from taking derivatives of our likelihood function. So that likelihood function contains it. We just have to integrate it, or derive it, not integrate it, get it out of there, right? So there's another LaTeX typo. This is a markdown typo right here. So the second derivative actually talks about the curvature of the log likelihood. And again, this information matrix comes from asymptotic theory, right? So remember, as n goes to infinity, this is what it should arrive to. Right? For any n that you observed, it may not be true, though. And here, if we look at this, we're doing maximum likelihood with the multivariate normal distribution. Well, let's build this as well. This actually should be a different slide. So this is all one slide here. This other part should have been a different slide, but I have a typo. So standard errors come from the second derivatives, information matrices. The same thing happens with theta. If you wanted the conditional standard error of measurement for theta, you figured out a person's information for theta, right, and took 1 over the square root of that information value. That was the standard error, conditional standard error. Same thing here. Right? All from ML, and you didn't even know it, right? Or did you? But you've seen it before, most likely. All right, let's talk about doing this with multivariate normal, because we know that multivariate normal is where CFA lives. And CFA makes, while this is not an easy function, it's a lot easier than figuring out what happens in IRT, which has to have an integral, right? But if we talk about maximum likelihood with the multivariate normal, here the difference between a univariate normal and a multivariate normal is now we have a vector of data for a person, and here this person's data has V, capital V for capital observed variables themselves. All right, so observed data here. There's our density or likelihood function. Now remember, the mean vector has all the means, covariance matrix. The diagonal of it has the variances. The off diagonal has the covariances. And that sigma has to be invertible because it shows up right here. Not only that, the determinant has to be bigger than 0 because you can't divide by 0. At least it's undefined, I hear. So anyway. So these are the parameters of interest. So instead of now having a single mean and a single variance, I have V means, I have V variances, and I have V choose 2 covariances to estimate. That's a lot, right? But they all come from the same likelihood function. So here's your multivariate normal density. I made this plot like in 2005 in MATLAB. I still love it though. This is for a mean of 0 in each dimension, a covariance matrix of 0.5, kind of a nice bell-looking distribution. All right. This is if I flew over the top of that distribution. By the way, this plot's going to come back again at the end of class. Flying over the top, these are likelihood contours, right? So that read those lines. Anybody goes hiking? You ever been hiking? Seen a contour map? Mountains talking about where equal elevation is. That's equal elevation, but just on a likelihood surface now. Right, so this is one way of representing it. All right, so let's assume, again, we go through the same process. We assume we know mean. If this is looking at the likelihood itself, the PDF, if we knew the mean, and the mean vector, and if we knew the covariance matrix, I could tell you a person that had these two scores had this height. A person that had these two scores had this height. So we would say that which one of these is more likely to observe with this mean vector and that covariance matrix? The one with the higher likelihood. That's all the likelihood's good for it. Right now, let's build a sample-based. Let's not do this. Let's build what we need to build to estimate the mean vector and covariance matrix. So here, we again go through the same process. We have the PDF for one observation. We have to multiply those PDFs, assuming independence and identical distributions. You've heard that before, but this is what really puts it into process. You probably, without taking statistics, heard independent and identically distributed IID before, right? This literally is why we assume it. We have to make a multiplication, and we have to put a distribution function in. If they weren't independent, well, we have models for that. It's called multi-level, right? Or SEM, or latent variable models. If they weren't identically distributed, well, now it becomes a mixture. All sorts of fun things we can do. But you can see why we say it. We're literally describing the mathematical process. And again, that same process happens. We have the product. That product looks really ugly. And then doing a little bit of algebra with exponents and so forth, we can simplify it a bit. But that's not pretty, right? That thing's ugly. And that's like the best it gets. Right? This is like if you do this for do the likelihoods for a living, you're like, yeah, the multivariate normal it's a thing of beauty compared to what you have to deal with in other places. All right, so this if we observe x, and actually I have flipped this as well too. This should be the likelihood of mu and sigma conditional on x, like my previous slide. I apologize for not having that. The reason why, you're going to see in a few slides though, why that keeps getting interfered with. That's our likelihood function. So we have to go and maximize that function itself. We could, of course, take a log likelihood. This starts to look more like what you see in, like if you go to user manuals of like SAS, go to like ProcMix, this starts to look like what's in the ProcMix user manual. Right? The breadcrumbs of how those methods work. And here is this likelihood surface. I had some data, I had 10 observations, and I played with some data back in the day. But what we can do is figure, if we knew the covariance matrix, we again could do a grid search and figure out where the mean vector happened to be. That's what that's telling us. Questions on this? So now, the question I asked Nathan at the beginning of the class, I'll ask to everybody again. How do you build a likelihood function? Start with the PDF for one observation.
Assumptions.
Multiply, that's right, assume independence.
Yeah.
If it's independent, you multiply those PDFs together. Maybe do some simplification. Now you have your joint likelihood, take the log of that joint likelihood. And that's how it gets built. Right? But it all starts with PDF. And this is why I'm tying, when I taught like IRT and I taught CFA this year, I was putting them in PDFs. If you remember, go back to like lecture 2 or lecture 3 or whatever, I taught that. Everything was about distributions, right? Guess why? That's the core input into our likelihood function. We need the PDFs to multiply. If we can write a PDF with our model in it, instead of these other random generic parameters, we now know what to do to estimate our model for psychometrics, and we get maximum likelihood out of it. Pretty cool, right? Okay, and by the way, you don't have to be an expert at calculus to do this. You may need a little bit of algebra, but even that, for what we do a lot of times now, there's a function in R for almost every distribution function, right? D-norm is the normal one. D-binom for binomial. D-POIS for Poisson, right? Every one of those fits into it. So depending on if you wanted to do a factor model with Poisson and you didn't have access to M plus or didn't want to pay for it, you could build a likelihood function and you could estimate it if you wanted to. I wouldn't advise it. I'd probably put it in days, but you could do it. Okay? Mentioned that before. Okay, useful properties. Okay, so here's some more useful properties of MLEs. You've heard of these before. Where have you heard of likelihood ratio tests before? Which class? Which class is? Anybody?
Generalized linear models.
Generalized? What's that, Alfonso?
Stat inference.
Stat inference. Anybody talked about it in IRT? No. We'll get to that in just a moment. Likelihood ratio tests can be used anytime you have maximum likelihood. Right? I'm almost certain, actually I'm not almost certain, I'm darn right certain Lisa's taught it too. Right? What is a likelihood ratio test? First of all, let's talk about what you have. You have two models, one of which is nested within the other. Right? So how do you tell if models are nested? Right? If you can make some constraints on the bigger model and you end up with the littler model, those are nested models. Parameter constraints usually, right? What do I mean by that? For instance, if we're trying to test a two-dimensional covariance, a two-factor model versus a one-factor model, and we have simple structure items, that's equivalent to phrasing a two-factor model with a correlation of one of the factors. Because if you have two dimensions but correlation of one, you really only have one dimension. Right? But that's a constraint we placed on it. So if you have these two nested models, you estimate both. The difference in the -2 times their log likelihoods will be a chi-square distributed variable. Again, this is built by asymptotics. Assuming a couple things, some of which actually pop up here. You can't have a parameter on its boundary. So that example I gave you where the correlation was 1, that's the maximum that parameter can be. That actually violates some of our assumptions. It makes it not exactly chi-square to compare it with. But the other place where that shows up is variance components. If you're trying to remove a variance, this is a multi-level thing. If you don't think you have a random slope, well, you fit a random slope model. The assumption that is now the random slope is the variance of the random slope is 0, which means it goes away. That's a nested model that you could do a likelihood ratio test on, but the chi-square is not the right distribution. It's actually a mixture of chi-squares. But anyway, so you've done likelihood ratio tests before. I know this. In Lisa's class, if you've taken her multi-level or some of her factor analysis, that's it. But this now allows you to test a null model versus an alternative. And get this, the constraints that you place to move from the alternative model down to the null is your test of hypothesis. The null hypothesis in my example is the correlation between these factors is 1. Written out, not in math terms, but in language, we'd say that the null model is that there's a single factor. The alternative is there's two factors. And now we have a regular setup for a hypothesis test that we're so familiar with the hypothesis testing framework that's been around for over a century now. It fits. But I'm out of time. It's break time. So I'll pause there and let you think about how magical that happens to be. But it's true. All right. Break. I'm going to hit the pause button on my recording. Well, sorry about missing that middle section, but this is the best. Let's talk about quadrature. All right, here we go. If we have some type of function here, just some type of function itself, if we want to integrate it, we can approximate that integral by creating little regions under which we could take these are easy to compute the area, right? And yes, we're off on the top, we're off on the bottom, right? There's going to be gaps and so forth. But as the number of these regions have a midpoint, that midpoint is sometimes called the quadrature point right there, right? And so with that, what we can control numerically is the number of those quadrature points. And what we can show mathematically is as the number of these points goes to infinity, our approximation becomes the integral itself, right? So if these points get smaller and smaller, what am I doing wrong? Did I do that wrong?
This is giving me, I'm flashing back to a project I didn't calculate.
Okay. There's a lot of ways of doing this, so
No, it was a good project.
that's good.
Good memory.
I didn't know, first of all, here's the thing. My self-confidence is such, because I haven't talked about this in a while, and when I work on this, if I'm coding it myself, I'm like in the tank, like I'm just like locked in, right? But like teaching it's something different. And so when I see the smile, it's honestly where I'm like, what's going on? I think you're calling bullshit on me, which is totally legitimate, and I will believe you. And that's where, like, when I see you smiling, doing it, I was like, what did I do wrong?
No.
What did I say wrong? Especially those of you who likely have more calculus background than I have. I'm looking at that. So, anyway, that's where it comes from. This reminds you of this.
Yes, it was a good, I'm a teacher.
That's
and
good.
It was a good lesson. So, sorry.
Yes. No, it's good. So, what do we have to do to numerically integrate? We have to determine how many quadrature points there are. We have to figure out the midpoint of each, plug that into our function, and then multiply that by the width or the area around it based on our quadrature region. Right? Did you talk about this in IRT? I think you did, maybe a little bit. Okay, it's the same thing. But we have to do that to estimate our model. So again, our likelihood function, and this is not a log because it's a product, but if I were to take the log of this, it would be the sum of the log of that numeric integral. And what we replace in this integral, we replace this integral right here with this approximation function right there. So it's the sum, or the log of a sum. Remember, the log of a sum is not equal to the sum of the logs unless something crazy happens, and I don't remember what that is. You know what I'm talking about, right? So it's, anyway. So, what that means is, this integral, even though I have one sign here, this is a vector, so it's a multidimensional integral if you have more than one theta. And I mentioned this in previous classes, but it's really true. If I have 15 quadrature points per dimension, that means instead of, I don't just have one sum now, I have two sums. If I have 2 dimensions, I have 2 sums. So if I have 3 dimensions, I have 3 sums. So what you're doing there is multiplying the number of things that you're summing up exponentially, right? So 2 dimensions squares the number of quadrature points. 3 dimensions cubes the number of quadrature points. We have this exponential increase in calculation. So doing quasi-Newton, remember quasi-Newton is figuring out where the peak of the likelihood is using some approximations to derivatives and stuff. You can do that, but the thing that hinders it in IRT, once you get past 2 to 3 dimensions, is any reasonable number of quadrature points will take forever because you have to calculate a lot. With 15 in one dimension, if I go to 2, it's 15 times 15. It's 125 per person to calculate over, right? If I go to 3 dimensions, it's 125 times 15 per person, right? If I go to 4, okay, you can see my point. Some programs even warn you. The number of quadrature points is, I think M plus says that. Consider using something else. So we're going to talk about a little bit of something else in just a bit, but first I'm going to dive into EM algorithm here first, okay? So EM algorithm, this is the classic paper for EM in our field, again, psychometrica. It's not a coincidence that psychometrica is where a lot of this stuff has been published. It's our premier technical journal in our field, right? It's where we study psychometrics. Darrell Bach, Murray Aitken, 1981, showed how to do EM in IRT, in the context of IRT. This changed estimation of IRT considerably. We went from using logist to using bilog. Darrell Bach had a student by the name of Bob Mislevy. There were other students involved as well too, don't get me wrong. There's a number of people who were good, but Bob Mislevy was involved in that. Mislevy is a giant in our field. I think he's recently retired, but he's amazing. I look up to him. That's what he was doing, right? So he sort of helped implement this in Biolog. Biolog, many of you may have used already. How many of you have used Biolog for estimated IRT before? Yeah, still there. 40 years old, but still going. So the EM algorithm, I will note first, still requires integration, and I'm going to show you why in just a moment. So if you're using EM to get away from integration, that's not going to help. We're still having to integrate. Basically, we start with an initial guess or an expected value. We calculate the expected value of latent variables. In the E step, we plug them in as observed, use an MLE at that point. The neat thing is, the theory of EM is that the algorithm is guaranteed to converge to a local maximum, which is also good, right? Turns out, the EM algorithm gets really, really slow as it approaches that maximum. And what you'll see, like M+ implements this, but other people will find ways to try to make it easier. M+ actually can switch. It'll do EM by default. And then at some point, as it gets closer to the maximum, you might switch to a quasi-Newton for a step or two, because you can interchange the two to try to speed convergence. But here's how EM works. Remember, to do E, an expected value means we need a distribution. So we have to define a distribution for theta, in this case a prior distribution. So using Bayes' theorem, we could say the distribution of theta given our data is here, right? This is our model likelihood. This is our prior for theta. This is a typo. It should be over the distribution of y, not theta down there. That's slide 69. My goodness, lots of typos today. Pardon me, I apologize. That should be y. Okay. So, that should be y down here too. So if we want the expected value, remember how we did expected values a while ago? I tried to give you that. I scratched that out with my pencil, I think. An expected value is the integral across the distribution of the value itself times what the distribution should be for it, right? So if you think about what it's doing, is it's basically weighting the numeric value of it by how likely it is to occur in a distribution. But this is how we do the E step. And again, here in the E step, we have to approximate this, right? We have to use numeric integration, quadrature points, all that fun stuff. So EM isn't going to help us when it comes to high dimensional models. And by high dimensions, I'm talking 4. Right? I think we can all agree 4 is not a lot of dimensions, but 4, right? What's that?
Is it just it takes a while?
It does. You've done this, yes. How long did it take, just anecdotally?
Well, when I did 3D, it took like 5 days. Now I'm on 40, it's taking like
5 days.
Yeah, it's really fast.
You got that, everybody? 3-dimensional model. How many items?
Like
20 some odd items, and not that many people, like 1,000 something, right? 5 days for 3 dimensions using EM, right? And now 4 dimensions, how many days is it going on?
It's still going.
Uh-huh. It may still be going into October, right? Yeah. So can we all agree that's a bad idea? How are we doing? Any questions on this? So there are a few shortcuts that people have come up with. They usually involve how we do integration. One of them involves how we do integration. One of them involves how we do, again, an EM algorithm. So the integration by sampling, that's for quasi-Newton. Could also be for EM if you wanted it to, right? Anywhere there's a integral. Turns out you can do Monte Carlo integration. Have you ever heard of that before? Here it is right here. I'll show you that in the next slide. All right? So we could basically sample values and use them in our integration process to figure out our integral. Just like everything else with the sample, we need a large sample. So, you know, every step of the chain, we might have 5,000 sampled values using that for our integration. The other way is to substitute the E step. Remember, E is expected value, right? And not only that, we're using Bayes' theorem to get an E out of it, which in Bayes' class we called an EAP estimate. Well, anything that gives us the E can be put there. In fact, we could change this and put in, for the E step, we could just, you take the parameter values that are currently at that step of the algorithm, plug them in as known, and create an MCMC algorithm to go and sample theta. We run our MCMC algorithm for a while, and we just get our expected values of theta from it, just like we would in regular MCMC. And we use those for our E step, and we do the M step the way we want as well. This is a very crude way of describing a paper that Lee Tsai had in 2010 talking about Metropolis, Hastings, Robbins, Monroe algorithm. This idea has been around a lot longer than that. Hybrid EM is sometimes what people will call it as well too. So that method is great because it cuts down again on the number of calculations we're doing. But the problem with these methods, though, is they're not exact, in a sense that now we're dependent on some sampling process. Now, do you remember in Bayes' class what we have to do to make sure the sampling process is maintained across computers or for replication? We have to have the same number seed, right? We have to have the same equipment. So it's possible that even if we have a different, depending on how it's built compiler-wise, underneath the hood, it's possible that we can have the same random number seed and be on different computing sources. I use Argon and you use your laptop, and we still may get different values. Similarly, if we want to do model comparisons with likelihood ratio tests. Now those are harder to do because they're not exact either. Right? So this shortcuts estimation, but it presents a whole lot of difficulty in a lot of everything else that we do. Any questions on that? By the way, this is Monte Carlo integration. Yeah, let's skip it. Okay, I just mentioned that. All right, there is one final method. It's called limited information estimation. In the history of psychometrics, this actually came before EM, and this came before anything we did in Bayes. This came straight out of CFA. This actually is what gave rise to the term IFA, item factor analysis, because this was the first methods used for people who were not in education, they're generally in psychology, to estimate models with binary data. And so basically the idea is this, that our categorical data is derived from this underlying continuous process. Sorry for this. This is not a typo. This is a typo. This tilde should be over y. But imagine if we have a binary variable where y is 1 or 0. We could envision that being the result of some underlying process such that right? So if we have this underlying distribution, we call this y tilde. And maybe we'll call this the threshold right here, this tau. And if anybody whose y tilde was above this threshold right here, their y equals 1. And anybody who was below this threshold, their y equals 0. You may have heard about this in Lisa's class when she started talking about item factor analysis, where you got into the binary data unit in the SEM class, right? Well, if we play that out, and we assume that the underlying y is normally distributed. This is a markdown thing that drives me crazy. If any of you can fix why my tilde is not centered over my y, help me out here. Or maybe Dr. LeBeau is the guy to ask. Tau is our threshold parameter. Y tilde is continuous and latent. What ends up happening is if we think of y tilde, which we can't observe, and we don't want to call it latent like theta is latent, we're going to call it unobserved. Right? Or underlying, the propensity for a y to be a 1 or a 0. But if we work with this pretend y tilde, then our model on y tilde is a straight factor analytic model. Right? So if we could have y tilde, we'd be doing CFA. Right? Because we saw under CFA, we can derive what the model implied covariance matrix is. So we know what a covariance matrix of our data should look like if y tilde was happening, and we have data for it. So now we just need an observed version of the covariance matrix. And we can go back to, you remember the CFA likelihood right here? If we had an observed version of a covariance matrix, we could put all of this together and use our CFA likelihood on it. That observed version of the covariance matrix is not really covariance at all, because this underlying distribution doesn't exist. But we can put some constraints on it, and we can get something like that. In particular, we could say that y tilde, not y mustache, y tilde, that looked pretty bad, right? Follows some type of normal distribution where the mean is 0 and the variance is 1. We can assume that. And now, our gosh darn it, drop everything. Now, we know that our covariance matrix, we call it S here, may have 1s down the diagonal for it, which is no longer, sometimes we call a covariance matrix with 1s in the diagonal a correlation matrix, right? So now it's up to us to figure out where do we get our correlation matrix. Turns out there's a great correlation that we use in psychometrics, something called the polychoric or tetrachoric correlation. You've heard of this before, I take it, right? You probably heard about it in intro measurement courses. Your very first measurement course, people will talk about the correlation between binary variables. Now, we don't use the Pearson correlation. I mentioned this earlier part of class when Jacinta talked about her investigation of your technical manual. Because the Pearson correlation with binary data does not have a -1 to 1 range. Right? It's actually compressed. But the tetra or polychoric correlation does not. It goes from -1 to 1. So what we do is we say the observed covariance matrix is the poly or tetrachoric correlation matrix. And then we use it in our CFA loss function to figure out what the model parameters are. And this is now a limited information estimator because we plugged in that observed covariance or correlation matrix to do this. So this was the first way. Now this gets away from the integral altogether, because the likelihood function from CFA over here doesn't have any latent variables in it. So therefore, we have this. Let's do a little bit more on the tetrachoric. Tetrachoric correlation is a measure of association between two binary variables. So if you have two category variables, this thing is tetrachoric. If you have 5-point Likert items, the same process happens. That's what we call it polychoric. So tetrachoric is for two category items. A polychoric is for items with usually more than two categories. Sometimes people call them all polychoric. The process is the same. What differs is where the categories are. So the correlation comes from mapping the binary observed variables onto these underlying distributions, the tildes. But, and with these underlying tildes, we end up having these thresholds, tau 1 and tau 2, that bisect in each dimension. We saw that in my notes here. This is one of the thresholds. It bisects it, right? It cuts it into two. Now again, this is for binary data. If we had multi-categories, we'd have more thresholds, right? That's the big difference. So next, what we have to assume is that if each one of these is univariate normal, y1 tilde and y2 tilde, then the pair of them is bivariate normal, or a two-dimensional multivariate normal. With me so far? The mean of that distribution has to be fixed at 0. It's unidentified, right? Y tilde is technically latent, and we have one observation to show it. So we got to start nailing parameters down. Mean is 0, so the mean of both of those underlying distributions is 0. The standard deviations of both of those is equal to 1. But if we do that, we actually have enough It's statistically identified to estimate the correlation, and that correlation is the tetrachoric correlation. Let's see it with data. Here's my sorry, with not just data, but with numbers a little bit more. So this circle thing in the middle is from the multivariate normal. That's our probability equal likelihood contours, right? So if we flew over the top of the multivariate normal mountain, this is equal heights, right? The lines here represent cut points. These would be taus. Okay? Now we have 4 regions, right? If we look at the x-axis here, this is like y tilde 1. Anybody to the right of the line is where y equals 1. Anybody to the left of the line is where y equals 0. Okay? And this is y tilde 2 over here. Anybody above the line is where y tilde 2 equals 1. Below the line is where y tilde 2 equals 0. So now, if you think about it, the multivariate normal sitting on top of that, when we have these two binary data, y1 piece of data, y1 and y2, we can form a 2x2 table, right? Where the number of people or the proportion of people who have each permutation of zeros and ones can be calculated, right? These 4 quadrants are the cells of that 2x2 table, right? This quadrant up here is for y1 equals 1 and y2 equals 1. This down here is where y1 equals 0, y2 equals 0. And the likelihood function that we need to build for this, which is your homework, by the way, smile at this because I promise this is a challenge, but once you solve it, you'll be a changed person for the better. That likelihood takes the shape of the multivariate normal. Remember, this is a multivariate normal where the center is fixed at 0 and 0, and the distance, like the variance in each dimension, is 1. But what changes is the correlation, and as the correlation changes, the angle of these ellipses change. Right? A 0 correlation has a big circle, right? Now, the area under the curve is what we need to align to the proportion of people in each one of those quadrants, right? And if you align that, then you find the correlation that maximizes that likelihood, linking the two together, you've got a tetrachoric correlation. So we're putting it a little bit more notation. I made these slides back in LaTeX using something called PS tricks, and that doesn't really transfer over well. This is also like in 2005. So 18 years ago and a lot of packages ago, so I just took screenshots. But here, take a look at this part of the table right here is where the first dimension is 0. I had alpha here, but it's y. So 0.69. That area under the curve that's shaded should be 0.69. Right? Or another way of putting it, the likelihood function for it, for a single observation, down here, is looking at the probability y equals 0. Turns out with this thing, the threshold parameter that we're looking at here for one dimension describes all of this. So it's not that important. So when you do your homework, ignore the thresholds. I should have put that. I'll modify homework today and I'll edit it to say ignore threshold. Just look at the correlation. Really what we can do is take 0.69 and know that it only applies to the x-axis down here, y1, and we can convert it over to what the standard normal version of it is, using an inverse standard normal distribution. But here's the key. This right here is your hint for what the likelihood function is. I have categorical data, right? I have a set of people who answer with a 0 and a 0. I need to express this probability using a multivariate normal distribution. Now I have 2 integrals in that distribution. All right? Now this integral, this whole multivariate normal, you don't need, I've got a hint in the homework, you don't need to do the integral yourself. I am allowing a package to be used for that. Okay? So there are people who have functions that will do this for multivariate normal. You can use it. But you see the mapping. What we want is the shape of that multivariate normal to line up such that the area in that quadrant is equal to the proportion of people answering where they would be in that quadrant. Does that make sense? Any questions on that? So this is what shows up as our observed covariance matrix in item factor analysis, though. And if that's the case, then we can take a function of our model implied and map it onto it to make the discrepancy function work. Now that function of it gets into a little bit more complicated stuff we'll talk about next week, because there's multiple ways. We have to make our model parameters, lambda phi lambda transpose plus psi, align such that the diagonal of the output is 1. And there's multiple ways to do that. Basically, we have to rescale them, because the numbers themselves may not be where the diagonal is 1. So we have to go and take what those numbers are, rescale them. And that's where different methods of rescaling happen. There's two common functions that M plus is named delta versus theta. You may have heard those terms before. That's where it shows up. Theta is the closest to what we do with IRT and full information. I won't go too much into those. Once we estimate it, we may want to use its numeric properties, but because we're not in full information, we can't directly use that. So sometimes we have to use some type of adjustments. In M+, there's a method called weighted least squares mean and variance adjustment. It's like the robust maximum likelihood, where you adjust the likelihood value from it. It also changes how we do model comparisons. So likelihood ratio tests have to use some type of scaled version to build it. I don't need to do that. Don't need to do that. And then there's Bayes. But I'm going to do this. I'm going to pop over to homework real quick, if that's all right. Any questions while I grab homework real quick? So I want you to try it on this. I don't want you to be too frustrated. And you're already smiling. But this is going to, the purpose of this homework is to help teach you maximum likelihood. Honestly, this was the problem that I didn't know I got hired to solve, which got me into diagnostic models. The very first algorithm, I got hired to be an RA for like in 2001, like late 2001, I think, early 2002. To work with Bill Stout, Jeff Douglas, and some folks at Illinois. They said, hey, we have this model, but we have this algorithm that works, but it's just isn't converging, something's wrong. And 2 years later, Bob Henson had this epiphany on the likelihood being wrong, and he figured out what the right likelihood should be. So that shows up a lot. But beyond that, I also found that once I figured out what that likelihood is, it sort of dawned on me a whole lot of how maximum likelihood works, and how what we do with psychometrics works. And so I want you to have that experience. That's my goal. It's not to put pressure on you. I'm giving you 2 weeks, right? And you can work together, right? Just be considerate of those who may not have a group, that's all. Basically, derive the sample log likelihood function for the tetrachoric correlation. I will note it is a discrete distribution. That's your hint, okay? Because the data are binary. We pretend they're continuous. Okay? So just note discrete distribution. I didn't know that before. The person who coded the algorithm didn't know it before. We learned this stuff, right? Then take that and put it into a function in R that takes as input just rho, the correlation itself. Just rho. And 2 binary variables. Right? So the input to the function is what rho should be, variable 1, variable 2. The output of the function is the log likelihood. Right? So you submit variable 1, variable 2, and some guess of correlation, whatever it happens to be. Out comes a log likelihood. That's what I'm looking for. The hint on this is that you cannot use any built-in functions that compute tetrachorics, but I would advise that you use the why is it P here? This should be the MVT norm package. Has a function called PMVN norm, which is how we estimate this integral right here. It's looking at, if you give it limits of integration, it'll give you the area under the multivariate normal. You can use it. It's great. It doesn't use quadrature, it uses a quadratic approximation. So it's pretty neat, okay? So then, take that function wrap it into a function that you submit to the Optim package or the Optim function. Because what this will do is it will search. You could think about it with your original function up here. You could do a grid search. You could look at values of correlation from -1 to 1 and plot the likelihood, right? And even figure out the MLE is. But I want you to use this Optim function to do it for you using one of the optimization routines they have. To do that, it takes as input this function and limits it to just having the correlation. So it's not that. This step 3 is just reshaping something to get it to be used with an optimizer. This process, by the way, is technical computing that you will, if you're in the technical side of psychometrics, you will get into this frequently in your career, more than you expect, right? To optimize things once you build a likelihood. So that's what that is. And then finally, estimate the matrix of tetrachoric correlations. Now I realize I didn't tell you what to use for the thresholds. So I will edit this to tell you what to use for thresholds. Because the thresholds are needed. Actually, no, the thresholds aren't needed. Oh, they are. Yeah, you need thresholds right here. The limits of integration are the thresholds. Right? Where that. So I'll tell you what to do with that. They're just simple z, proportion to z, cumulative normal distribution function. Not simple, but I'll give you the function for it. What do you think? Will you accept this challenge? Who's scared? It's okay.
Everyone.
What?
You can't not accept the challenge.
Well, you could. You could be like. By the way, I forgot to mention to you, you can drop one homework. I'm not lying. I'm not lying. And I don't know what's coming next for homework, but I think the rest of the homework in the class will be applying the multivariate methods to data with different packages. So you'll get more practice in working with data. There will not be the analytical results that I'm doing here. Yeah, Vladimir.
Yeah, I have 2 questions. So we don't have like a data, step 1 is step 1.
Mm-hmm.
Okay. How can we know that we are doing well?
You may test your function by simulating data.
Oh, okay, yeah.
So that brings up a question. How do you generate data from this? I'll leave that to you to try to figure out. But I'm available for help, certainly over email, and I have office hours.
Great.
Next question.
Yes. We don't have any kind of template or example.
No.
Okay. Great.
No. I want to challenge you.
Great.
So, if I were to give you recommendations,
And
start with that likelihood function first. Communicate with me what you think about it. In fact, Friday's office hours, give it a thought before Friday and come to office hours if you want to bounce it off me. Come, office hours are online now. Join me on Zoom. The link is in the icon. Okay? That would be my recommendation. I'm your scaffolding and my slides.
thank you.
Okay. Plus, there's lots been written about tetrachoric functions, but I want you to try to discover this on your own. Okay?
Yeah, of course.
All right. Anybody else? All right. It's been a pleasure being your instructor today, giving you good customer service.
My cookie.
I'm not that good. Have a great rest of your week, everybody. Take care.